Okay, so thank you for the introduction. So today I would like to talk about the scientific application at the Budapest University of Technology and Economics. I'm an electrical engineer, so I'm not an expert in GPUs. And I would like to show you our research that we did and are still doing on the stability and vulnerability of power grids. My colleagues, so you can see on my presentation, have been working on this project quite some time now, and I just recently joined that project. So what we are interested in is how vulnerable power grids are, what are their stability measures, and how robust they are. And in order to investigate this, we implemented the Kuramoto oscillator model. Now you have to know that the Kuramoto oscillator model is a bit resource intensive. That's why we decided to introduce the GPUs into our project. Okay, so let's start with a quick recap on power grids. Sorry. How can I move the slide forward? Okay, thank you. Okay. So quick recap on power grids for those who are unfamiliar with these. Obviously, power grids are an essential infrastructure today for our civilization because they transmit the electrical power that we use for almost everything. Traditionally, power grids were primarily powered by these electromechanical generators. So these generators work in a way that they supply a bit of stability to power grids, but lately these power grids are under a lot of pressure because of thanks to the spread of renewables. And these renewables, like solar panels or wind turbines, they are quite volatile, so they unstabilize the grid. Okay, so this unstabilization leads to the frequency of outages and blackouts growing lately. Let me tell you how we model the power grids using the Kuramoto model in order to investigate these outages. So the Kuramoto model is a system that can simulate all kinds of networks in the real life, and the Kuramoto model sees these networks as a set of coupled oscillators, meaning that it abstracts a real life network as a graph. And in terms of power grid, this graph is made up of nodes that correspond to, for example, substations and power plants, and even consumer nodes at the leaves of the graph. And the nodes, the edges of the graph are the power lines between these nodes. As I told you, the Kuramoto model has oscillators at every node that are coupled. And in normal operation conditions, the power grid, the power grid is node has roughly the same frequency under normal operating conditions. And in case of, like, for example, a storm or any irregular activity on the grid, this stable synchronized state can easily just blow up. For example, if there's a power line cut by a branch or by a storm, and this line failure, this line shutdown can then spread throughout the whole graph and cause like a cascade phenomenon and maybe a huge blackout or huge outage. Okay, so let me formulate the Kuramoto model mathematically. So on the slide, you can see for each node of the graph for each oscillator. And as I told you, the Kuramoto model sees the graph as a sort of coupled oscillators, and oscillators are characterized by their phases, phis. And in order to investigate how stable the network is, how synchronized it is, we need to follow the change of these phis for each node over time, which means that we have to integrate this equation. For this, we use numerical solvers. And also you can see from the equation that each node's phase is mainly affected by the neighboring nodes' phases, as you can see from. So each node is only affected by neighboring nodes. The A matrix is the admittance matrix, which is just a fancy word for adjacency matrix, essentially. And I also told you that there's a Kuramoto equation we need to solve for each node. And as far as power grids go, they can go up to tens of thousands or even millions of nodes if we want to investigate a more complex network. And in order to be able to follow all nodes phases, we introduced the GPU to start our investigation and our implementation from scratch. We already have an implementation. Our colleague, Dr. Kelling at Dresden, already have a GPU implementation of the Kuramoto model. And he also had a talk about it at the 2019 GPU Day. It's a very good talk, so I highly recommend it to check it out. The main points we have to know about is implementation, that it implements the second and the first order Kuramoto models, and we can use it for any graph we want. It abstracts the GPU using the Vexial library, and it already has a numeric solver for the equation from the Boost numerical library, but he only had the Runge-Kutta fourth order numerical solver, which is a simple implementation. And the main, I think the most interesting part of his work was the special memory layout he used to store the network graph for the GPU to efficiently access the data. I won't go into detail today, but you should check out his presentation. It's incredibly interesting. Okay, so, but in order to use his implementation, we needed to introduce some new functionalities into our system. For example, the most important one from these is the line failure modeling, which I talked about. When the graph desynchronizes, it can. And we also use some higher order integration schemes in order to be able to tune the accuracy of. Okay, so that we integrated from summary, and I won't go into detail, but here on this slide you can see the comparison of the runtime of these numerical solvers. As you can see, for example, that the BS, the Boolean store solver, is the one that has the least runtime in terms of the overall benchmark runtime, which means that this is the best solver because all the solvers are tuned to the same precision. However, paradoxically, this Boolean store solver had the largest runtime per integration step, which is because it's the most complex of all the solvers. But it is able to quickly solve our problem. It is thanks to its complexity. It thinks a lot about what order to use, what integration step size to use, but then it probably makes the right decision and can quickly finish. Okay, so another the blackouts, as I already mentioned. So you have, in order to understand how power grids work, you have to know that power grids have these overcurrent line protection systems built into some of their substations and the nodes. And what it essentially does, it detects if the power flow between the nodes rises above a certain threshold level. And if that happens, it basically shuts down the entire line. Now this shutdown can, as I've already mentioned, spread to other nodes and then cause this massive blackout. I will just quickly walk you through how we try to simulate power grid behavior. First, we do the thermalization, which is just a warm-up process. We let go of the network and let it synchronize. And after the thermalization finished, it's basically in a normal operation condition. And then we perturb the network by removing a couple of nodes. And this removal is enough to, for example, start a blackout, start this line failure spreading all over the graph. And during this process, we measure important measures like the Kuramoto order parameter. So the Kuramoto order parameter shows us the overall synchronization of the graph. You can see on the visualization on the left side how a system can look when to the left it is fully desynchronized. All the phases are spread around from 0 to 2 pi. And if the network is synchronized, the phases gather together into close to each other. And in case of the synchronization, this Kuramoto order parameter is around 1. And in case of desynchronization, it's 0. Okay, so here you can see some preliminary results of our research. For example, on the left, we can follow how the order parameter changes during, for example, this one of the failure cascades. We also use different threshold values for cutting the lines. And as you can see, at the beginning, there are many lines that fail, but as we approach the end of the simulation, the system mostly synchronizes. I mean, not synchronizes, but gets to a steady state where the phases of the nodes doesn't really change anymore. Okay, we also I also plotted some other measures, important measures for different network sizes and different initial conditions. We still have a long way to go. So we still want to run a large number of parametrical studies in order to reach some conclusions about these power grids in terms of statistical physics and network science as well. Okay, to summarize my talk, I wanted to give just a quick insight into our research that was about the stability of power grids using the Kuramoto model to simulate the power grids. We already have a GPU implementation. We just introduced some new functionalities in order to be able to simulate power grids more. And okay, so this is the end of my presentation. Thank you for your attention, and feel free to ask questions.
Thank you very much. Questions, please?
Very good talk, thank you. So I'm wondering, with your simulation, you can analyze what happens if something fails. Is there any way to come up with interventions or responses to limit, for example, a cascade, to stop it getting even worse?
Yeah, unfortunately, if a line fails, it is not advised to switch it back on immediately. The best thing we can do is analyze the network statistically and understand which lines probably are the most vulnerable and come up with ideas on how to make these networks more robust in the long term. But immediately, no, we cannot really intervene. Gesa?
Let's speak up, please.
Yeah, maybe I can comment on this because our plan is also to study the spontaneous feedback. If you look at the Kuramoto, there was this dissipation term. This dissipation term is very similar as having spontaneous feedback. So you want to check what's the effect of spontaneous feedback. And in the later terms, we may also study
Other quick questions? I would have one, maybe I didn't get the point. So what is one oscillator in reality? Is it a substation?
Yes,
or is it
it can be a substation, even a power plant. So
or
these
a
are of
passive
different
line
sizes.
is also, or the so passive line is a constant something, yeah? So it's part of the line is. So I can imagine you can have a thunderstorm somewhere in along the line. So this means that you have the oscillators at a certain substations and nothing between.
No, any node. So nodes are any intersection between the lines where two lines meet, a substation or like a individual consumer or a transformer
So you have
station.
something like 4,000 or like that. What was the number of
nodes of so a typical power grid can be of varying sizes. It depends on the complexity of our model for the power grid, but it can go up to 1 or 1.5 million of nodes.
And there's a reality, for example, for Hungary? Or?
Sure.
Oh, okay.
Yeah, absolutely. Yeah, we are planning to run this on Hungarian power networks. Yes.
Yeah. Okay. Thank you very much.
Thank you very much.
Thank you very much.